Hello everyone, I'm really glad to see you all coming to my talk. And this topic about time allocation and time intervals maybe not close to everyone's heart. Maybe not all of you will face it in your daily programming jobs, but still this is useful in a lot of problems. So I hope a lot of you will grab something interesting from my talk today. So in the beginning, I would like to say that my company, Evolution Gaming, is hiring people. We are a growing international company that has a lot of offices in Europe, and we hire engineers in 3 of them, which are in Amsterdam, Riga, and Tallinn. So if you're interested, you can come to our booth in the main hall, and we can discuss things we do in Scala, for example, event sourcing with Akka persistence, some Scala JS projects, and a lot of other interesting things. So feel free to come and discuss. A little bit about me. I'm working in Evolution Gaming for more than 2 years. Maintain a little bit, a little set of date-time related projects on GitHub. My overall experience is in Scala is around 4 years, and so last 2 years in Evolution Gaming I've been developing a scheduling system which basically exposed me to the things I'll talk about today. Excuse me. So Spire is a huge toolkit of mathematical abstractions. I'll be talking today only about one tool, which is intervals and interval sets. But if you're doing any kind of math on your daily job, you should definitely take a look at Spire. It has a lot of really neat things. These are core maintainers of Spire library. So I'm really grateful to these guys for creating this project. This really made my life a lot easier. So kudos to these developers. So let's start. First, I would like to cover some theory, just in case some of you may not be familiar with that. So intervals are pretty simple concept. We'll take a look at real intervals, which are the most kind of commonly known example of intervals. So interval is just a set of numbers which is defined by 2 boundaries. Each of them is either closed or open, where open boundary is a boundary that doesn't contain the value at the boundary itself, which is an empty dot on the graphical representation. And the closed boundary is the opposite of that. It contains the value at the boundary itself. And there are special kinds of boundaries which are infinity, positive and negative infinity, which represent unbounded intervals. So also there is special empty interval, which is equivalent to empty set, and the degraded interval that contains only one element, basically a singleton set. There is one interesting property about intervals, which is you can't iterate all the members of an interval. So even a very small non-degraded interval contains an infinite number of elements, so it's an infinite set. So, and to kind of overcome this, to iterate, you can introduce some precision, for example, like some 1,000ths, but this will not be an interval anymore if you do that. So, and this is kind of similar to what we can say about time intervals, because given a non-empty time interval, you can't possibly iterate all the moments. Because like that's kind of doesn't make any sense. Interval sets is a natural extension of the idea of interval, right? So it's just a set of intervals that are joined using union operation. So again, it's a set of numbers, yeah. So there are some examples, pretty straightforward. Just the same thing, getting more general. Let's go over some operations. The most commonly known is intersection and union. So all the operations I'm going to look at are not specific to intervals or interval sets. It's set algebra, just regular set algebra. So these are examples of intersection and union. I think most of you should be familiar with that. So intersection is taking a common part of two intervals, and union just joining them together, taking all of the elements in the resulting set. Another interesting thing is complement operation, or inverse in other words. It's just creating, given some interval set, it creates a new interval set which contains all the elements that were not included in the original one. So that's also very useful. And the last one we're going to look at is subtraction. No examples here because this can be written using already covered operations, which is basically if you want to subtract set B out of set A, you just intersect A with a complement of B. Right, so we covered operations. Now just let's quickly look at what problems are solved with intervals. The most common application of intervals is to model uncertainty. So we are functional programmers, and we know one data structure that models uncertainty, which is list. So instead of one result, you can get a 0 or several results. All right, so this is kind of uncertain result of a computation. Intervals model different kind of uncertainty, where list is discrete uncertainty. You get some finite number of discrete values. Interval models a continuous uncertainty, where your result lies within some range, but the number of possible different results is infinite, right? So that's kind of useful in a lot of problems. There are other applications of intervals, but today we're going to look at scheduling, which is related to time. And the reason we can do that, we can use intervals to work with time, is because actually intervals don't require anything numeric from the underlying type. The only thing that is required for intervals to work is order, total order. This is kind of Katz's order, or you can take standard Scala ordering. So the Spire intervals work with Katz's order, but you can in general use any other order type class you know about. So intervals require order. Let's bring them some. There is some caveats with implementing order for datetime values. One of that is the main is that for zoned datetime values, for example, Java time, zoned datetime from Java 8, you can create two semantically different order instances. They are completely lawful, but they are different. Let's take a look at them. So first one is strict order, which is comparing values including the time zone. So if you have two identical instances, they have to be located in the same time zone to be equal. Even if you have identical instance, but they have different time zones, they will be considered not equal. This is kind of the strict one. There is a relaxed version of that, which is also lawful, where we compare only instance. So, for example, if you have different time zones, but the instants are the same, these will be considered equal. So, depending on your task, depending on your problem, you can select either one. They're both legit. They're both lawful. So, given we select one of these order instances, we can create intervals of like time intervals, right? That use date time values for the points. Now, now we're ready to look at the code actually. So let's start with bounds. This is a very simple ADT, right? That just to encode the data. So there are open and closed boundaries, which contain a value and just represent, as it says, either open or closed boundaries. And there are two special kinds of boundaries, which are unbound, that depending on the position in the interval encode either negative infinity or positive infinity, and empty bound to encode empty interval. Right, so the interval itself is conceptually just a pair of bounds, as we discussed, but the encoding is a little bit different, so you don't have any public ADT here. This is done for performance reason, for kind of safety reasons. There are several design considerations in this choice, but instead of ADT we have several smart constructors, and they are pretty much enough for everything you might want to do with intervals. Right, so, and as you can see, they all require order implicit to work. So let's just cover the interval API. So if given you have a single interval, what you can do with that? So you can do a lot of things. You can check if a particular point, in our case a datetime value, belongs to the interval or not. If you can check if two intervals, one interval is a subset or superset of another interval. You can calculate intersection and union of two intervals. You can also, like with union, it's a little bit tricky, right? Because if you have two disjoint intervals, the union will be an interval set. So that's why I'm not listing it here, because we didn't get to interval sets yet. Complement and subtraction operations are also, I separated them in a separate point, because in general, when you do these operations, for example, let's take subtraction. If you have a big interval and you subtract a small interval from that, you get two intervals instead, like as a result. So in general, they return these operations have to return a list of intervals to work for all cases. This is kind of inconvenient, and this is a sign that we are working in with a too low level abstraction. So we'll see how this will be solved in interval sets. And there is interval arithmetic APIs, which we'll not look at today, but these are also very, very useful. So we clearly see some limitations with interval, and if we need union, complement, and subtraction to work more in a more general way, we need interval sets. These were developed by Rüdiger Klein, and actually this is a very nice piece of software. I would say really had no problems working with these things from day one. So thank you a lot for developing these things. Interval sets go into two flavors. First is interval trie, which is under the hood is represented with a tree. It's really fast. It's the fastest of two, and like the performance doesn't go for free. To work with interval trie, you need a really fast isomorphism to long. So basically, your underlying type has to fit in 64 bytes, and the conversion should be fast for you to really gain some performance from that. But this constraint is actually not a very tight constraint, because if, for example, if you use time, you can still use milliseconds precision and you will fit into long. So only if you need nanoseconds precision, you will have to resort to more general representation of an interval set. So that's not a big requirement in most of the cases. So the interval sequence is a more kind of general representation, which is an array. It's a little bit slower, but it's still very fast. You can check out Rüdiger's talk on the details. So he goes there really deep into implementation details of how these things work. Really interesting talk. Really recommend this to watch. So and the results show that the interval sequence is still very fast, given the rich API that it provides. So finally, we are ready to do some real work with intervals. Let's take a look at a problem that I guess most of you face every day, which is calendar scheduling. So let's say we have 3 employees which have some work already scheduled, and we need to squeeze in a meeting of 1 hour long somewhere in their daily schedule. And the meeting has to happen in the working hours from 9 a.m. till 7 p.m. So here the task is quite simple. We can actually solve it with our eyes, right? So there's one kind of space where a meeting can be placed and another one. or no, I guess at the bottom, right? So yeah, we can solve it by hand here, right? But as you can guess, when the amount of people is bigger, when the schedule is more complex, the solution might not be that obvious. So we'll try to solve the task so that it can be easily generalized for more complex problems. So let's start. We'll begin with some helping code, some aliases and helper methods. So entry, basically schedule entry, right? It will be a single time interval. Entries will represent a interval sequence, basically a time interval set, a set of several non-intersecting intervals. Union all operation will convert a list of intervals into a interval sequence. Basically, interval sequence is isomorphic to a list of intervals, so we can go back and forth, but for some reason Spire doesn't provide this this arrow of the isomorphism, so I just wrote it here. Backwards, so from interval sequence to a list of intervals, there is a method that provides this API, so we don't need that here. And the duration is a simple helper to calculate the duration of an interval. It's an option because we can't handle all kinds of intervals. We can calculate duration for an empty interval, for example, or a degraded interval. So that's why it returns an option. The implementation is kind of not optimal in any way, but it's enough for our purposes here. And we need duration because we need to filter the results so that the meeting so that the interval is at least 1 hour long, so that we can feed the meeting inside. The next thing is we need is to load the entries, basically to load the existing schedule entries for the employees, the ones that were displayed on the picture in the beginning. So in the real world, of course, we'll get them from some external service or from database, but here we'll just write them out as lists. Workday is a simple interval that represents the the working hours from 9. This daytime is just creates a daytime value on some day that I selected under the hood for this task. Basically a 9 a.m. until 7 p.m. and the duration is just a cached duration of 1 hour that we'll need later for filtering. So now we are ready to solve the task. So first of all, we'll join all the entries for our 3 employees, right? We concatenate all the lists, and we'll union them all into single interval sets. This interval set of basically this interval set will represent all the intervals where at least one person is working, right, from them. So and this will be the time where we can't have a meeting, right, because somebody is working. And on the second step, first we invert the someone occupied interval set, right, to get the interval set of periods where nobody is working. This is what we need, right? This is the set of all time periods where nobody is working. We intersect this. So intersection is this in Spire, this end Boolean end operator. We intersect this with a workday to get the periods that belong only to a workday. And the last thing we need to do here is to filter the duration so that smaller intervals don't get into results for the possible meeting places. So we materialize the interval sequence, interval set to a list of intervals. This is the part of the isomorphism that is provided by Spire. And we filter them by duration. So we say that we need only the intervals for which the duration exists, and that duration is more than 1 hour long. So, and if we run this, we get the same result that we obtained basically manually, right? I have an example running, so you can basically go to open this link and launch the Scasti worksheet. So this all works. Yeah, you can play around and just try some other tasks. Second thing we'll look at is kind of this, again, calendar scheduling, but a little bit different this is more of like analytics related tasks. So we need to see for some period, like let's say 2017. We need to find all the periods where Alice, Bob, and Charlie were working at the same time together. So we need kind of to find the correlation between their kind of calendar entries. This is again very, very simple to solve. First we'll do kind of, it's almost the same thing we did in the first task, but here we don't merge all the entries together in a single interval set, but instead we'll create interval set for each employee. So basically we just convert all the lists to interval sets so that we can work with them using Spire. And then we just take each occupied is so we start with a set of all values. Basically this interval sequence all is a minus infinity to positive infinity, and we start to intersect this using again AND operation with the sets we have. So basically what this means is we intersect all the interval sets together to get the common part of all of them, all of these three, and this will be actually our result, what we want. So that the set of intervals where all three employees work together. So let's kind of step aside and see. So we had this in our union all, right, which is fold left using union operation, and in the last example we had again a fold left using intersection and starting with a interval of all values. This thing like looks similar, and they look familiar, right? So we probably have some abstraction here that we can use, and the abstraction turns out to be a monoid, and not only a monoid, actually this thing is called bounded lattice, which is kind of mathematical term. To explain that in a kind of more approachable words, bounded lattice provides join and meet semi-lattices. Each of them is a idempotent commutative monoid, basically. So what it gives us as programmers that we have two set monoids. Again, this is not related to intervals or interval sets specifically. It works for all sets that come from a common superset. So we have a negative infinity to positive infinity, which is the power set of all intervals, right? All the other intervals are a subset of that. So when we have that construction, we have two monoids, which one of which starts with empty set as an identity element, and the union operation as the addition, and another monoid is this this common power set as identity and intersection as a addition operation. So that these abstractions really help to use kind of like not write a lot. We can like eliminate a lot of boilerplate and use already working code from CATS and Spire that uses these instances. So back to our problems. There is a huge space of problems about resource allocation. So one example can be allocating people to some work that has to be done in specific periods. So we can take some grocery shop or another publicly working business that needs some people to do some work, not by the volume, the amount of work, but the to work for some time. So that's a very tricky problem to solve in general, and there is lots of various kind of the variety of different problems, different aspects of these problems is really huge. So there are lots of minimization problems you have to solve. So the general idea is to match, right, the work and the resources and the requirements, right? So in some optimal way, and the optimal is defined in each task a little bit differently. So in some problems you need to minimize overtime. In some other problems you need to comply to some local legislation and so on. So there is like the spectrum of these problems is really wide. So it's hard to provide some really simple example that shows shows these problems in general. So instead I'll just provide a small kind of piece of solution of these kind of problems. So this is kind of an attempt to solve resource allocation problem where requirement is a interval set. So we again here use our aliases from the beginning. Requirement is an interval set of work that needs to be done. Basically, this requirement will say, so I need a 8 to 15 shift every day, like someone to work here. And the work is actually the list of people who will work, like the actual schedule that is currently active. So John works at day 1, like Alice works at day 2, and so on. And given these, we can quickly calculate a set of important metrics for our solution. For example, which time was covered, so which part of requirement was actually covered by some work. Even more important, which time was not covered. So basically when our cashier desk is empty, when nobody will stand here. So this will quickly show, this is like, you can see this is a one-liner with Spire. And we can see unused time, where basically wasted resources, where some person comes to work but doesn't do any useful work because there is no requirement. And like this is just an example of how simple solutions can be for really complex sounding problems. And that's by using Spire. Yeah, so another dimension of real-world applications of Spire is integration with the domain, because the Spire intervals are purely mathematical thing, and most of the time you don't need that in your domains. It's actually very good that people start to pay attention to relation between application code and business domain. And this is really great. You can see that by recent rise of popularity in DDD, domain-driven development techniques. People try to maintain their ubiquitous language very well. And yeah, I tend to agree that that's really great. And this is why I raised this topic here, because Spire is not a good fit to be placed directly into your domain code, because it's math. Most of the time you don't need math in your domain. You need some real business-related terms. So the problem is that, right, intervals and interval sets are too broad for most domains, because I would say that 99% of real-world domains that need time intervals, they don't require negative infinity, for example. You can't represent anything with negative infinity, anything useful. So most of the domains would actually do pretty well with just bounded value intervals on hand. And so the problem is that when you're able to instantiate something that doesn't represent anything useful in your domain, you're creating problems for yourself, because these values now need somehow to be handled. And so your programs ideally must be able to represent only the values that are valid in your domain, right? So that's why you should seriously consider separate domain suitable data structures. Basically, you will have some business-related data that will, under the hood, use Spire for performing this complex calculation, and this will give you like total freedom in controlling what kind of values can be created. Also, you can simply maintain your ubiquitous language and gain other really nice benefits. So the only drawback, of course, is that you have to maintain your own set of data structures. But that's I think the benefits outweighs the drawbacks here. Right. So that's kind of what I wanted to say about integration with domain. This is very important, so that your math terms don't leak into your domain terms. Another several concerns that I have my Slides are broken. Okay, so another concerns about integration with domain that I wanted to go over is that, yeah, this I already mentioned. What kind of intervals make sense in your domain? You should think about that really carefully, because this may require you to throw exceptions if you don't handle that properly. Another thing is what kind of bounds do you need in your intervals? This is also very important, because if you're not careful with bounds, you can have degraded intervals. So when you have two intervals that are adjacent, and at the adjacent edges you have two closed boundaries, you get intersection returns you a degraded interval with one value. So if you don't need that, you need to take some consistent approach to boundaries. For example, the one we took in my project is to create always, so the left boundary is always closed and the right boundary is always open. In this case, you won't get any degraded intervals ever using any kind of operations available. Another thing to consider is time precision, not only because of the domain concerns, right? So your domain might not need nanoseconds or milliseconds, but also like more coarse precision may allow you to use faster interval trie data structure, which is also a benefit. Ordering and equality, I discussed that in the beginning of the talk. So you might need strict ordering or more relaxed equality that uses instant comparison. So this is also a thing to consider. And try to avoid leaking Spire terms, Spire types into your domain, so that business people reading your code don't have to like ask you what is semi-lattice, like what a monoid is, and stuff like that. So yeah, that's basically all I have. Thank you, Scala Days, for inviting me, and thank you all for coming. And we have time for questions, right? Good. Yeah. Do we have a microphone for?
Thank you for the presentation. Could you give a couple of other useful examples of sorting, except the time? I mean,
of using intervals?
Yeah.
Okay. So there is a slide about, let me scroll, about problems that are solved with intervals. Various kind of fuzzy logic is very useful application. So for example, expert systems, they use a lot of fuzzy logic. So basically your result of your calculations lies in some range. So basically you provide, as a result, you don't provide a value, you provide some range. So this is basically the kind of scheduling is a side application. The main application is uncertainty. So if you want to provide your users, or like whoever calls your API, if you want to provide some range, this is a way to go, because yeah, you can, because Spire allows you to operate on these ranges. So there is interval arithmetic, for example, and you can look that. So I would say mostly it's kind of science, but also for a very, very complex system, there can be multidimensional constraints, like and it's also, so for example, you have some interval set of allowed values on some, for example, you have a manufacturing facility and you need to check some metrics of some devices, like so that they lie in some ranges. So that's also a useful application, for example. Like, yeah.
I've used exactly this thing, not this one, but something in Java that was equivalent.
Okay.
And that was a SLA requirement, and we had like systems that were down and up, and so the time thing happened a couple of times in my life, and hopefully it will happen a couple of times to others too.
Yeah, yeah, great example. Yeah, thanks. here in the middle.
Hi, thank you for the talk. And do you have a way in Spire to represent something higher dimensions, so like rectangles, and to use all, you know, the...
You mean like multi-dimensional intervals like that, or?
So like seeing like a rectangle that is a product of two intervals?
I don't think so. Yeah, I don't think so, but yeah, I don't think so that, that there is something like that. Actually, I would ask you in return, like what kind of applications, just out of interest, what kind of application do you
So yeah, we had a use case quite recently about using time, so in 2 dimensions. So one was the time when the user was trying to access something, and the other dimension was the time the content was published.
Okay.
And we had to do something similar, but basically with rectangles instead of intervals. So using all these algebraic combinators and check the intersection against the union.
Sounds cool. Sounds really cool. Thanks.
Thank you.
Does Spire provide its realization format? Because the common problem is, how do I put those in my database?
No, of course not, because like serialization is a totally like orthogonal concern, right? So there are only these data structures. The way you want to serialize them is like completely up to you. So if you want something out of the box, I think there would be a problem with intervals because they are not there is no public IDT, so you'll have to invent something like by hand, because like the commonly known, for example, JSON libraries, they would not derive your some codecs automatically because there is no public IDT. So answering your question, no serialization. Some other questions? Yeah, they're also on the back.
Hi, is Spire able to resolve optimization problems like convex optimization, linear optimization in such a context?
There are some. Actually, as I said, Spire is a really huge toolkit. So I didn't like dig into all the kind of branches. So it has a lot of different kind of branches of problems solved. There are some. There are some algorithms there for sure. I've seen some like gradient optimizations, I guess. So, but I haven't explored that side of Spire. But you should check that out. There are lots of things you might find something of that, like it's not something useful. So there are definitely some algorithms inside, but I'm not like I haven't discovered like a lot of haven't explored that area. So couldn't really say.
Yeah, hi. Thank you for presentation. So I would like to ask about the if you use some real application, how about performance? Because on unlimited bound for plus or minus, I think we'll have a lot of computation. Thank you.
Yeah, performance is really well, and actually the encoding of these intervals is really concise. So you don't, for example, if you take interval set, right, you don't need to store all the values because the amount of values is infinite. You store only the kind of points. So if you draw the interval, like the line of numbers, right? So your basically interval set can be represented just as a array of points where there is some boundary, and you just need to encode what happens at this boundary. Well, like, does the interval start or does the interval end, and if it's a closed and or open boundary, and that's it. So and the amount of computation is also really small. So if you're interested in this problem, you should definitely watch this talk by Rudiger. Where's that? Yeah, this fast immutable interval sets at Scala World last year. He goes into detail, so the representation and amount of work that needs to be done to do all these calculations is really small. So that's the point.
Just to the question serialization, I think it's relatively trivial to come up with a serialization with it, because we have a kind of a sorted list, and it can be empty or something, and then we have the 3 types of boundaries. We have the upper and the lower can each be under any of the 3, and in 2 of the cases you need a value, and that it's extremely trivial to find a database representation or a JSON or XML or whatever you like, but it's not out of the box.
Totally correct. Yeah, so the actual the actual data that needs to encode, that is needed to encode a interval set is really small. So you just need the points and the type of these points. That's it.